market, a game theory analysis. ASOS, Boohoo, and Misguided are just three of the thousands of purely online retailers now commonplace in today's clothing industry. Online shopping has seen extraordinary growth, and the Financial Times reports that in December 2012 the market share of online sales of non-food items was 11.6%, which more than doubled to 24.1% in the following 5 years. The global online fashion market was worth $533 billion in 2018, and is predicted to grow to $872 billion by 2023. This industry is highly relevant and something I often use myself, hence this project. This video will look at the scenario of a customer looking to purchase a t-shirt online. The customer has come across a t-shirt he would like to own which he values at £30, and it costs the retailer £10 to create it. It is currently on sale for £30, however the shopper knows that there is an upcoming sale where selected items will be discounted by 2/3 of their original price. The payoffs of the customer and the retailer are as follows: 30 minus Y for the customer, where Y is the price the customer pays for the t-shirt, and X minus 10, where X is the price the retailer receives for the t-shirt. If the t-shirt is not purchased, this gives the customer 0 payoff, and the retailer a negative 10 payoff for not selling the item. If the customer buys the t-shirt for full price, their payoff is 0, and the retailer's is 20. If the t-shirt is bought at the discounted price, payoffs are reversed. In the case where the customer waits for a sale but the t-shirt isn't discounted, yet he still buys it, the customer receives a -5 reduction in their payoff from disappointment of not buying the t-shirt straight away, as they could have had it earlier for the same price. Some key components of the strategic interaction include the players, which are the customer and the retailer, the preferences of the game, which are ordinal and based on the player's payoffs, these terminal histories, which specify sequences of the game from beginning to end, and the player function, which assigns each sequence that does not end with the terminal history a player whose turn it would be to move after that sub-history. Some assumptions are made to simplify the game. Firstly, the game is a sequential game, meaning that players move one after another. We also assume perfect information, which means that each player is perfectly informed of the history of what has happened in the game so far, up to the point of each of their moves. For example, the retailer will know if the customer has bought the t-shirt or not by the time they decide whether to discount it, as they either will or won't have sold it. This simplification applied to the real world represents that the retailer might have a surplus stock of an item by the time a sale came around. If they haven't sold what they needed to, they can decide whether to discount it or not. We also assume that the retailer can predict the customer's reaction to either a sale or no sale through analysing past sales and customer trends. We assume rationality, which means that each player's ultimate goal is to maximise their own payoff, and for simplicity, we assume that there is only one retailer and one customer. We use backward induction to solve this extensive form game. We use this method because we have a sequential game with perfect information, meaning there are no simultaneous moves. The game is also a finite horizon game, and so backward induction is an appropriate solution for these reasons. We first looked at the subgames to perform this. In the subgame, we see that the customer would choose to buy the t-shirt if it was discounted, as a payoff of 20 is greater than 0. In the second subgame, the customer would choose not to buy the item if they had waited and the t-shirt was not discounted, because a payoff of 0 is greater than -5. This results in the subgame now shown. The retailer would decide here to place the item on sale as to receive a higher payoff than they would for keeping it at its normal price. 0 is greater than -10. This is often seen in the real world, when stores lower the price of an item in a clearance sale to minimise losses from unsold items. The reduced game is now shown. The customer would choose to wait for the sale as the payoff they receive is larger than buying immediately. 20 is greater than 0. The outcome of this wait, buy, and sale price results in a payoff of 20 to the consumer and 0 to the retailer. The solution is a Nash equilibrium, since neither player has an incentive to make any different moves given the other player's moves. It's also a subgame perfect Nash equilibrium, as each subgame is a Nash equilibrium. Game theory can be applied to many real-world situations and can be used to predict how strategic interactions should logically plan out. However, I have also found that modelling real-world scenarios with game theory relies on making many assumptions, some that might be quite far from reality. In our example, we modelled that there was only one customer and one retailer, whereas in reality there are an abundance of both, and customers can shop around for the best deal, as well as they have the option of buying second-hand, while retailers have to compete with each other. Also, perfect information might not exist as fully as we have assumed in this example. In conclusion, the game we have created in this video has helped to analyse the actions of customers and online retailers when planning strategies for buying and selling in relation to an upcoming sale. However, the conditions and assumptions in the model have taken away some of the real-world elements. However, changing these could lead to unrealistic and illogical outcomes.